I was just also thinking to you, I don't think we'll need that common, or that they're still in the car or something. Yeah, George has just said to me who's actually in, I was like, that's me and Sam.
You could do the alternate.
I did it on the spectra, because I couldn't work out a way to download what you have free. It said I already had it, I'm like, well, no, I don't.
I forgot, so I'm going to do it after.
Yeah, I did mine on SketchUp, it's not too bad. I've been using SketchUp since I was like 11, so I did it in like, it straight. I said, there you go, boom.
Which room you're usually in for the concrete design? 2 hours after this.
After it's down here, it's
J123.
1, 2, 3. Okay. So our extra class should be here because it's so under that one.
We've got coursework due today, so that's probably why people aren't coming in.
Oh,
Design of concrete coursework's due.
it's today.
it's today.
I don't know how many people you're going to get.
Okay, we will start anyway. I was thinking maybe the bus is late, but we just start. We cannot wait more. It's 2 minutes past. So obviously you have done your coursework, don't you?
Yeah.
So if you remember, we spoke last week about how we did just a quick recap. Anyway, you're the third person who have done your concrete coursework probably.
Yeah.
Because you're here.
Yeah.
We have a lot of absence today.
Yeah,
for
the concrete coursework.
Concrete coursework, yeah.
Obviously, I'm one side of the class, so you can explain just one side. The other side is happening anyway.
I will teach you that. So what we have done last week, if you remember, we solved a single degree of freedom system for an earthquake input. So we had ground shaking, like an earthquake, and we solved a kind of partial differential equation, and we succeeded to calculate this function, which is the deformation of that single degree of freedom system. So we have an input and we have an output. So this is the output in terms of displacement of that single degree of freedom system. This is the case for any kind of oscillator, if it's single degree of freedom system or multi-degree of freedom system. And today I'm gonna talk about how these stuff will influence the real structure and how this goes to the Eurocode. This is a very important session today, and you will really see how all of these stuff will go directly to the Eurocode 8 for seismic design, seismic loading, and how these concepts work for analyzing some real structures, and we'll assess the dynamic behavior of some real structures as well. Just again for a recap, we used the earthquake input last week as a set of data recorded by some instruments like these. These are very early generations of accelerometers. They are not very early generation. This is the second generation actually. And they are some units. They are really small. They are like this size, and they install it somewhere, not somewhere, many places. Like this is California, and we know the ground faults. These are the faults. The fault means a discontinuity between two ground plates, and usually earthquakes occur around the faults. So when we know the future earthquakes will be somewhere around the faults, so it's rational to go there and spread the instruments like as you see, they spread instruments along the fault. If any earthquake happens, all of the instruments will record the movement of shaking of the ground. And with that records, we can better understand the behavior of the Earth as a planet as well. So this is the source that our recordings come. So that's, just to be clear, last week when we talked about this one, these two columns are coming from these instruments recording earthquakes. This is time and this is acceleration of the El Centro earthquake. And as you can see, the time increment is 0.02. It's very small, very precise. In every 2/100 seconds, the instrument has recorded the movement of the Earth. So it's a very precise data to be used for structure analysis. And here is an example of different earthquake recordings around the world. Each has a name, usually named as the most important city or something like that near to the origin of the earthquake. It's San Fernando, El Centro, Parkfield, mostly from the United States. Chile, this is from Chile, not the United States. And you can see they are all acceleration versus time. They are all acceleration versus time. If we zoom in, you can see this is acceleration in terms of g versus time for one of the earthquakes. It's Imperial Valley earthquake. And for any movement, when you have acceleration, you can integrate once to come up with velocity, and you can integrate once again to come up with a deformation. You know, every movement, I'm moving. I have a deformation, I have a velocity, I have an acceleration. I can have an acceleration. It can be zero if I'm moving with a constant speed, for example. But any movement can be represented by a vector which has acceleration, velocity, and deformation. So if those instruments are reporting the acceleration, we can simply calculate and integrate to come up with the velocity and deformation. And vice versa, because there are some instruments not very common for other purposes, they are able to record either velocity or deformation. If you have any of these alone, you can calculate the other two. So if you have this one, you can calculate the derivation. Derivation of this will be this one, derivation of this will be this one. And from top to bottom, it's integration. So this is the input coming from ground shaking, and when ground shakes, structure responses to that shaking. So if we have a very simple structure as a single degree of freedom system, it will start to shake, to move, to oscillate. And we have an input, which is ground shaking. We have an output, which is the structural output, a structural deformation. Structural deformation, we have structural deformation. Any deformation has velocity and acceleration. And this is an example why structural deformation is important. There are two structures beside each other, somewhere in Mexico City in the earthquake, during the earthquake of 1957, a tall structure and a smaller one, shorter one. There was not enough space between these two structures. They're just touching each other, and it's called impact of two structures, or pounding. It pounded into each other during the earthquake and caused some local collapse here between the structures. So if the structures are very close together, it's more likely to have pounding effect during the earthquake. So that's why in most design codes, that's necessary when you're constructing your structure. You have a neighbor, you have two neighbors. You should construct your structure like this. You need to have a gap between this neighbor and this neighbor. Otherwise, you will have pounding during the earthquake.
Just like a medium joint.
Yeah. So that's why it's important to understand how we can calculate the deformation of these two structures if you want to do that. And these deformations should be limited in a way that they don't pound during the earthquake. This is another example. You can produce these examples with the Excel spreadsheet of last week. For example, this is the response of a system, single degree of freedom system, with natural period of 0.5 and that 2% damping. Any kind of single degree of freedom system can be represented by a natural frequency and damping system. And you can see if your system changes, like this is another single degree of freedom system, the response will be changed, although the damping is kept as 2%. So the response for a certain earthquake for two different systems is different, right? You have a single degree of freedom system with 0.5 seconds, you have a single degree of freedom system with 1 second, the response are different because the natural frequency is different. Although the damping is constant. If it's 2 seconds, the response is quite different. If you obviously change the damping as well, it would be different. Okay? If you change the damping, it would be different, and if you change the natural frequency, you're really talking about a different system, and the response will be different. So, what I want to say that damping is really a complex thing to speak about, and we can keep the damping constant for, let's call, steel structures or concrete structures. For steel structures, it's really 2-3%. And for concrete structure, we call it 5%. Sometimes for every structure, we call it 5%, because it doesn't make a big deal for what we want to do today. And good morning. Welcome to the private class. So. The idea is we want to see how we can represent these kind of deformation or response. We call the terminology response to any kind of either deformation or velocity or displacement. Response is a general terminology to represent the output of your structure. It can be displacement, it can be velocity, it can be acceleration. So when I say response means the output of your structure. When I say deformation response, it means that the output of your structure in terms of deformation. You can have deformation response, acceleration response, velocity response, energy response, shear force, internal forces response. Response is a general terminology to represent all of these stuff, all right? So obviously you can see that the response here is deformation. The response is different for different single degree of freedom systems. If the natural frequency changes, the response is going to change. I want to see how I can represent this change for a wide range of single degree of freedom systems. If I succeed to do so, it's a very important thing, because after that, if you have any sort of structure, I can give you some approximation based on your structure. Because if your structure, very complex one, has a natural frequency equal to 1 second, I can say this single degree of freedom system, very simple one. It's just M and K with Tn equal to 1 second. This is for this one. Okay? If you have a very complex structure with natural frequency of 1 second, I can tell you your response will be really very close to this one. That's the point. So I'm trying to see if I can, represent this kind of response for a wide range of single degree of freedom systems, right? Before I do so, I want to emphasize again that the whole response of the structure is not as important as the maximum response is. Because this is a response, this is a deformation. If you, for this single degree of freedom system, if you multiply this deformation by stiffness, deformation by stiffness, what you will get? Force, right? And I can just multiply all of these data by a constant k, and I can show you force versus time, right? And what force I usually design for? Maximum. I usually design for either this or this, because absolute maximum, or maximum absolute, because it doesn't make a difference if it's positive or negative. Positive means it's moving this way, negative means it's moving this way. So positive and negative, you should go for the absolute value of the positive and negative. In this case, for example, the absolute maximum is here. It's the negative one. And if you take this number into account and multiply it by k, the stiffness, you will come up with the design force. The thing that the codes need to do to deal with, to propose to the engineers to design for. We want this force. You will see this will go to the Eurocode. But the maximum one, we really don't need the whole history of deformation. We need the maximum one. Okay? So the question is how we can represent the maximum deformation to come up with the maximum force later for a wide range of single degree of freedom systems in a unique context to be useful for the design code and the design engineers. So here we are. Before I go there, I do a graph. I want to plot something, okay? Suppose that the x-axis is Tn, natural frequency, and for example, here is 0.1, let's call it. This is a single degree of freedom system with 0.1 second for Tn. If my system, single degree of freedom system, is a little bit taller, I will get 0.5, 1 second, 2 seconds, 3 seconds, right? I put different single degree of freedom systems along the x-axis. They are different in the natural frequency, and all of them have a constant value for the damping. Let's call it 5%. The 5% damping is valid for all of them, but they are different in either mass or stiffness, which means that it can change the Tn. So I'm representing a wide range of single degree of freedom systems, okay, in the x-axis. For a certain earthquake, like El Centro, today we'll work with El Centro again as a continuation of our work from last week. I will apply the El Centro earthquake to this one, the first system, the first structure. I will get the time history of the response. This is U over time, isn't it? We have done this. Last week we really did, this is El Centro. El Centro over time. This is El Centro as an input, this is output deformation over time. Okay? This part was what we have done last week. Today, we are going to say what is the maximum of this, absolute maximum. Please plug this absolute maximum here, wherever it is. Okay? Last week we have done this part for one single degree of freedom system. Today we are going to say do this and take the maximum one and put it here. Repeat this for all the other systems. Exactly the same procedure. I'll center as an input to the second one, get the response history function versus time, get the maximum one, plot them here. If you go there, you will have a graph like this. This is what I'm telling you. You will have a graph. The x-axis is Tn for different single degree of freedom system. The y-axis is capital D. Capital D means maximum deformation. In this book, U0, when 0 comes to any parameter, it means the maximum as a convention for this book. So U0 means the maximum of, for example, like this. U0 means maximum of the absolute of the UT. Or D, we're calling this my D. Okay? So the vertical axis is representing the maximum deformation. You can simply multiply it by K for your system and get the design force. Go and design your structure. This is how we can transform dynamic to static. We can transform a reality dynamic behavior of structure to a single scalar static force for the design. What we usually used to do in structural analysis, structural design, or any kind of design. Today you have concrete coursework, don't you? You're doing that right? And what are you doing in that coursework? You have the design force, right? That's a number, that's a force, that's not a function of time. It's not dynamic, it's static, isn't it? So that static force comes from here, if you have lateral load for seismic load, for example. So it's the maximum of the dynamic response, the maximum of the deformation. We will later multiply it by K to come up with the force. We call this a spectral deformation response. We called it a spectral deformation response because it's representing the response, the deformation response, for a variety of Tn, for a variety of, for a spectrum of natural frequencies. That's a spectral, this is a spectral deformation response. ST, we call it ST. A spectral deformation response because it's representing the deformation for a variety, for a spectrum variation of different single degree of freedom system with different Tn values, right? And you can see that the taller structure you have, please mention, note here, here, this is low-rise, this is high-rise structures. Why? Because, as I told you in last lectures, a 1-2 story building has a natural period of 0.1, 0.2. A 20-story building has a natural frequency of 2 seconds. So here we are talking about low-rise structure, small ones, short ones. Here we're talking about high-rise structures, tall ones. As you see, when you go from low-rise to high-rise, the deformation is increasing. So the maximum deformation is increasing. And this is understandable in a way. I forgot my ruler today, but if you have a very long ruler, put a mass at the top, if you just start to vibrate it, it vibrates like this. But if you have a very small structure, it vibrates like this. Right? So the taller structure you have, the maximum response, the more maximum response you will get. Right? So this is the spectral deformation. In a few moments, we are going to go to the Excel spreadsheet and calculate this for the center earthquake. But before that, before we jump into the Excel, I want to stay here to say that this is the spectral deformation we talked about in the previous slide. Okay? And it's really this one, Umax, isn't it? Right? Because this Umax will be multiplied by K, and you will come up with the force value. However, I can play a little bit with this formula in a way to introduce something very important. We know that omega n is square root of K over M, isn't it? We can rearrange it to say K is M omega n squared, right? And put it here, okay? I substitute this one instead of K here, so this is K. And Umax is the same, okay? I can say this is M multiplied by omega n squared Umax. And I call this one SA, or spectral acceleration. I don't want to, we're on record, I don't want to say non-precise thing. If I want to be precise, it's pseudo spectral acceleration for some reasons, but forget about pseudo. It's a spectral acceleration, and the dimension is something like meter over square second in terms of acceleration, because this is radian over square second, and this is meter, so the whole term is meter over square second, which means it's a kind of acceleration. And usually, for some reasons that I will tell you right away in a few minutes, we like to work with this one instead of spectral deformation. It's okay if you want to work with that, but as a structural engineer, I don't like to work with this one. Forget about velocity, I'm not going to talk about velocity. I like to work with this one, spectral acceleration, which is omega n2 spectral displacement. If you have your spectral displacement, it's easy to calculate the spectral acceleration, because in the previous slide, for any point you had spectral deformation and you know omega n because you know Tn, so you can just simply calculate the spectral acceleration. The reason that I don't like to work with spectral deformation and I like to work with spectral acceleration is when you want to design your structure, it's very easy. If you have your spectral acceleration, it's very easy just to multiply your spectral acceleration by the mass and come up with your force. Stiffness is a little bit tricky. Stiffness, I need to calculate the stiffness. It depends on the support conditions, on the connection of beam to columns, and many other stuff, right? It's not very easy. It is not very difficult, but there are some big uncertainties to calculate the stiffness values for some reasons. But the mass is very clear. Mass is mass. You can just calculate the weight of your structure, come up with the mass. Mass is very straightforward. If you have your mass, it's easy to multiply it by spectral acceleration and you will come up with the force and you can design your structure. That's why we like to work with the spectral acceleration instead of spectral deformation or the spectral displacement. So, here I want to freeze the slides. I want to go to the Excel. I've prepared you with an Excel. This is a continuation of our work. The first Excel is still valid. Please note. Whatever we are doing through this semester from the first Excel is a continuation of a continuous work. So last week we worked with El Centro earthquake for a single degree of freedom system. Today I'm going to use that as a continuation to come up with a spectral acceleration response. Let's see what we have. Just to recap, last week we had this one. This is for last week. We had this input. This is the El Centro earthquake. This is the El Centro earthquake. And last week we did these calculations. We had these formulas. We had these two from the earthquake, and we calculated this. This was the deformation, and this was U dot, the velocity. We don't have to do anything with this. We just need this one. We calculated UT, and we plotted here. This is UT versus time. UT comes from these formulas, and what we really did is we solved a certain single degree of freedom system with a constant damping ratio for a certain earthquake, and we plotted this UT deformation as a function of time. We are going to repeat this, and we are going to grab the maximum, the absolute maximum of this for our spectral acceleration and spectral deformation response, right? So this is from last week. And today, we are here. All of these are, let's start from the end sheet to the first sheet, okay? It depends on your taste, you can just rearrange it. This is exactly the sheet as the previous week lecture. This is El Centro earthquake. And this is exactly the sheet of the previous week. What I just did is, if you remember last week, the only difference from this sheet with the last week is, the last week was, for example, 1.3, about that bridge, remember? Everything was about that bridge, mass and K. We have mass and stiffness, nothing more. The mass and the stiffness were just for that bridge. And the difference here is, this is not for that bridge. I just put 0.01 second for Tn, and I'm just going to repeat this for many other cases. And for this Tn, I calculated the corresponding stiffness with the simple formula of this one. If you have Tn, it's 2 pi over omega n, right? Omega n is square root of k over m, okay? If this is 0.01, then you have your mass, calculate 3k. Just find the k. If you have your mass, I kept mass as a constant. The mass is exactly the mass of that bridge. Okay? I kept the mass as a constant. I played with Tn with different values. For this sheet, 0.1, 0.01, and I just calculated K. Okay? Vice versa, it means that for that pair of K and M, you will come up with Tn equal to 0.01 second. Right? So, here we are. What I did is changing this and correspondingly correct this. And I added these two. How I did that, I just calculated ST spectral deformation. If you take a look at this, this is the maximum of this is the maximum of absolute values of the whole function, you know. We just calculated this one. This is the response of your single degree of freedom system with that Tn, and I just got the maximum, which is here. Okay? If I get the maximum of the whole function, everything is in terms of feet, it would be this number. The maximum is this number in terms of feet. And I said I don't like to work with ST. I like to work with SA. That's why I calculated SA here simply by multiplying the above number by omega n squared. I have omega n here squared. This 32 point something is just because the dimension is feet over square second, and in terms of feet and second, the g, the gravity acceleration, is 32.7T41. I just divided by this number just to better show it in terms of percent of g, not feet per square second. It's okay, you can not do that. You can represent it in terms of feet over square second. But it's better. We usually used to represent spectral acceleration in terms of the percent of g. So if I represent it in a percent of g, if you want to work with feet, you can multiply by 32. If you want to work with meter over second, you can multiply by 9.81, right? So I got SA here. This is the SA, which is the maximum, coming from the maximum response. I repeated this sheet, you can see, for I think it's 18 cases. You can repeat it as many as you want. You will get more precise plots. The more point you get, the more precise plot you will get. The other sheets are just a copy and paste of this sheet. Nothing changes but Tn. Only everything is there, only Tn changes. For example, the next sheet is for T equal to 0.05. So you see, I just changed this one. Everything is still there. Nothing, I mean, the calculation will be different because they are linked together. So when this changes, omega n changes, everything changes. K changes automatically. You just need to change Tn and everything will be updated. You will get a totally different value for SA. And you just repeat this sheet, this spreadsheet for whatever you want actually. I just went for 0.1 second, 15 to 0.2, 3, 4, 5, 6, 7. And I went until 3 seconds. Okay? I went until the case of T equal to 3 seconds, which is enough, I think, because 3 seconds means for a structure, for a tall building like 20, 30 stories, that's enough. We are just looking at a wide variety of different buildings, so that should be enough. But theoretically, you can go until 5, 10 seconds, whatever you want. Then, the key point is here, spectra. How I drew this, this is a graph representing the x-axis is Tn, and the y-axis is pseudo-acceleration, spectral acceleration. I just did like this. I have 18 sheets, right? I just got 2 values from each sheet. And they are this value and this value. This is your x-axis, this is your y-axis, this one. So you have 18 points. Each point has an x and y, aren't they? So the x is this one, the y is this one. If you have 18 points, just connect the points together to draw a graph, right? So we have 18 sheets, and we just got 2 points from each sheet, SA and TN, and these points are coming from those sheets. Yeah, they are 18. And this is the spectral acceleration for the El Centro earthquake. It means that for any structure you have, you tell me what's your natural frequency of your structure. You say, okay, I have a very sophisticated building, but I've calculated the natural frequency of the building. This is your coursework. This will be your coursework. How to calculate the natural frequency of a sophisticated structure like a frame structure. This will be your coursework. But if you have your natural frequency of your structure, you say, okay, my natural frequency of the structure is 1.5 second. I will tell you, wait, 1.5 second. I can promise you, this is some kind of approximation for any structure. Your structure is 1.5 second. Okay, go here. You're around 0.2 spectral acceleration. Get this number, 0.2 G. You need to include G as well, whatever unit you're working with. G is 9.81, for example, if you're working with SI. This is your spectral acceleration. Multiply this with your mass, whatever mass you have. I don't care what kind of stiffness you have, because you have a lot of stiffnesses in different stories, in different parts of your structure. Whatever mass you have in your structure, grab your total mass, put it on a scale to see how much your structure weighs, and multiply the mass of your structure by this number, and you will get your design force. Design your structure for that force, and you will be safe. This is the brilliant idea of the design codes, including Eurocode. We will go to the Eurocode to see how does it work. I'm not sure today or next week, but after this discussion, we'll go to the Eurocode, and you will see that the whole thing, the whole concept here is employed in the Eurocode 8 to load your structure. Okay? Any question? So this is the first Excel sheet. This Excel sheet helps me to calculate the spectral acceleration for a specific earthquake. Okay? We'll keep it because still we are going to use it for some reasons. Here we have 4 examples, simple examples. Each has a very deep understanding point of dynamic behavior of structures. Bear with me, and we will see how does it work in terms of some simple structures. Okay? These simple examples really help to better understand, deeply understand the dynamic behavior of structures. Let's read what we have in the definition of the example. A 12 feet long vertical cantilever, this one, 12 feet. 4-inch nominal diameter standard steel pipe. This is the section presented here. It's a hollow section, steel one, circular tube. Inside and 4.026 inch outside, so the thickness is 0.237. The thickness, this is T. And second moment of inertia, something like I, we have I, although you can calculate it with the diameter and T. Elastic modulus is this one, it's a steel. And weight is this one. Determine the peak deformation and bending stress in the cantilever due to L-center ground motion. Assume damping equal to 2%. We want to calculate if the L-center earthquake occurs, what's the peak deformation of the system and the stresses inside. And then we can imagine, we can compare the stresses with the allowable stress, with the Fy, with the yield stress, to see if it's safe or not. This is what we want to do. Okay? The point is, this is a good representative of elevated water tanks. We had some examples in this module, elevated water tanks as well. I'm not sure, but this is a really good example, and it's common practice in UK, if you noticed. Elevated water tanks, they have some usually concrete, they're not steel usually, they're concrete columns and a very big water tank at the top, right? Just to supply the water pressure for the residents around the region. So this is a very good example of those kind of structures. And let's see what happens.
What's the use of making a water tank in that height?
To supply the water pressure, because it's not flat everywhere. It's like here, for example. It's a hill. Somebody live here. You have two ways. To construct a pump station here, to pump the water for everyone, but this should continuously working, and you need power, too much electricity and stuff like that. The second solution is to put some water tanks around, and you once pump water to the tanks and turn off your stuff here, your pumping stations, and they are going to the residence with the gravity. They are up at the residence, you know, they're elevated. And when it's going to be finished, they pump again. Okay? So you don't need to continuously pump water to everyone. Right? So you can supply water pressure for everyone with this trick. So, first of all, we want to simulate this system with a single degree of freedom. And for that purpose, for any system, single degree of freedom system, we need 3 parameters. Damping, we have it, 2%. Mass and stiffness. Mass, the water mass is 5,200 pounds. Okay, the water tank there, we're assuming probably it's full. And the weight of the column is 10 pound per foot, which means you have 12 foot, you have something like 100 something, but you can neglect the weight of the column in comparison with the top weight. It's not a big deal. It's okay, but you can add it to the top water, top mass as well if you want. But for this example, it's neglected. So the mass is the weight over G, So it's just using 5,200 pounds. This is the mass. Simple. The stiffness here is simple as well because it's a cantilever. And from this module, if you remember, we had several examples in the past lectures that for a very simple cantilever, delta will be, if this is P, delta will be PL3 over 3EI, which means P is 3EI over L3 times delta, which means this is K. This is the stiffness. Stiffness for cantilever is 3 EI over cubic L. We had this in several examples in this module for cantilever system. So you have E, you have I, you have L, you can calculate K, and this is your K. Okay? Any single degree of freedom system can be represented by damping, mass, and stiffness. Okay? If you have mass and stiffness, you can calculate the natural frequency. Just note that I'm aiming to calculate natural frequency. I'm really going to my Excel sheet to read spectral acceleration and bring that spectral acceleration multiplied by mass and get my force, design force. This is what I'm really going to do. So if I use this formula to use K and M to calculate omega n, and Tn is 2 pi over omega n. You can simply, if you have omega n, you can calculate Tn. Omega n is in terms of radian over second. Tn is in terms of second. Okay? So for this example, Tn is 1.59 second. When you come up to this point, stop there, and let's get to memorize 1.59 second. This is your natural frequency. Let's go to your Excel. Actually, the book is doing this with this one, but forget about this graph. This is a special graph representing the spectral acceleration, spectral displacement, spectral velocity, all in one graph with some techniques. We are not going into this problem. We are neglecting this. We are going to our Excel. We are using our own Excel. So just keep in your mind 1.59 second. Let's see what we will get from Excel. This is my Excel. This is the spectral acceleration for the L center earthquake. We calculated for the L center. 1.50, what was it, 59. It's somewhere here, isn't it? Right? Somewhere here. Something like a little bit less than 0.2 G, right? So I'm going for my own Tn, which is 1.59. It's somewhere here. It's a little bit less than 0.2. Let's call it 0.2 G. Okay? This is the spectral acceleration. This is the number that if you multiply it by the mass, you will get your design force. Let's get back to the book. If you realize, the book has taken 0.2 G as well from that graph. Because it's from L central and our Excel is from L central as well. We are doing the same thing. Keep in your mind, this is spectral acceleration and this is mass. If you multiply 0.2 G by your mass, you will get your design force. And 1.04 kips is your design force. And also, not to forget, did you submit?
Yeah.
If you're reading the spectral acceleration from the Excel, which is 0.2, always spectral acceleration is omega m2 spectral displacement. We had this in 2 slides before. If this is 0.2, you have omega n is here. You can calculate ST, which will be 5 inch. ST is 5 inch. And ST is spectral deformation. Spectral deformation is the maximum response. Because it is asking about determine the peak deformation. The peak deformation during the earthquake for this system is 5 inch. And the peak force, which comes from the peak spectral acceleration, is 1.04 kips. These two are occurring in one time. And that time corresponding to the maximum value of that graph in the Excel. So, if you want to design your system, now you're allowed just to use this number as your force. This is your force. Analyze your system, whatever you want to do. What's the maximum bending for your system? Where it occurs. If you have a force like that, 1.04 kips at the top. What's the internal bending moment at the top of your system? It's 0 here. This is the bending distribution, isn't it? At the top it's 0, it's a cantilever. At the bottom, the bending is maximum. What's the value of the bending moment at the bottom? Is the force multiplied by the height, right? So if you multiply 1.04 by 12 inch, you will come up with this internal bending moment, and that internal bending moment is something produces internal bending tension stresses in your section, right? How you can calculate the stresses, because it's asking about bending the stress. So bending the stress from structural mechanics. Can you see this? I don't know how to bring this aside. This is sigma max. Sigma max means maximum of stress. MC over I. M is bending moment. C is this one, half of your section. M is the bending moment, 12.48. C is half of your section. C is half of your section from neutral axis to the top of your section or bottom of your section. And I is second moment of area. You have I is here. So if you put everything together here, you will come up with 46.5 KSI as the maximum bending stress in your steel section. It's easy to do it, but KSI to megapascal. Just Google it. We have 46.5 KSI. It is equal to 320 megapascal. Is it okay or not? It's a steel. Is 320 megapascal okay for a steel structure or not? Your third year, you had a steel project, you should know what is the acceptable FY for steel.
GPA.
GPA?
Yeah.
What is GPA?
Should be bigger than such.
No, it's FY, not modular elasticity. It's FY, the yielding stress of steel. The modular elasticity is usually gigapascal.
Isn't that 435? It's got the characteristic strength of 500.
That's for concrete,
It's like concrete.
wasn't it? 500, you used to divide 500 by 1.15 to get 435.
Yeah.
That's concrete. It's okay. Build a concrete structure. Yeah, let's get back to the. If you remember, obviously you don't, but we had different grades for steel. The most common grade was S235. You remember? The grade steel 235 was the name, but it means that the FY is 235 megapascal. You have some upper grades for this steel to have something like 340 and 400. But usually you use ordinary conventional steel, which is 235. You could have some high strength steel to satisfy this kind of stress. But assume that we are using, or we don't want to pay too much. We are using steel, ordinary conventional steel. And the stress, the allowable stress, the yielding stress is 235. Obviously, this is more than that, isn't it? And this is not acceptable. This is not acceptable. What you should do as a designer? This is a design project. We have done this for El Centro earthquake. The resulting stress is this one. You want to really construct this water tank. What should we do to solve this problem? Because it's not okay, it's not safe.
Sorry.
Are you good?
Yeah.
So what we should do?
What should we do?
Yeah, what we should do?
We should continue the lecture, I think.
Good. Just to recap for you only, because we have a private class, we have a few. We solved a design project, okay, for El Centro earthquake. This is an elevated water tank, okay, it's made from steel. And we solved something, we came up here, the stress is 46, which means 320 megapascal. The allowable stress, Fy for the steel, is 235. It's more than the Fy, which means that this is not safe. The section is a hollow steel section like this, and the height is 12 feet. The question is what we should do as design engineers, structural design engineers, to solve the problem. The problem is the resulting bending stress is more than Fy. What should we do? It's obvious. The answer is obvious.
Go higher strength steel, higher class of steel.
Yes, that can be one solution, but as I said, we want to stick with this kind of steel. We don't have that kind of steel in the market for now.
Change the cross section.
Change the cross section. Go for a bigger one. Bigger your cross section to have more moment of inertia, second moment of inertia to decrease sigma, right? Use a bigger section, you will have more I in the denominator, you will decrease sigma, right? You do the same thing when you want to design your beam or column. If it doesn't work, if the ratio is more than 1, the safety factor, you need to bigger your section, right? Let's do it. We repeat this process don't be proud for your answer because it's going to be spoiled in a few seconds. We repeat the whole process with a really bigger section. This is the thickness, this is the eye. It's 72, the previous one was 7, 10 times more. The eye was 7 something, now it's 72 something. 10 times more eye, a huge section, okay? A very good section. This is not nothing but repeating the whole procedure again for this new section. And we came with 49 KSI. We had 46 KSI. The stress didn't decrease, even increased. Why? The solution didn't work. The solution was rational. I admit the solution was rational. The bigger your section, we didn't have any choice. We should do bigger our section, but we did this and the section is bigger now, but the maximum stress is even more than the previous case. The reason is, any idea for the reason?
As the moment is the same.
No, moment is increased. Because it's 68, the previous one is...
I think that's why.
Go and take a round and come back. You don't need to sit here. You know everything. Think so. You want to go to the cafe? Yeah, the moment is increased, and that's a very good answer, but not the whole picture. Why it's increased? If you answer this question, why it's increased now in this second trial, I will say you're a talent. You can go to the British Talent. What was it? America's Got Talent. British Got Talent.
What's happening with the mass?
Mass is constant.
Mass is constant.
If you want to take a look at the previous sheets, it's okay. I can just change to you can see the numbers. You can see the numbers. If anyone says the answer,
because C increases as well.
C increases, but it doesn't make too much difference. It's a little bit.
Is it because there's more mass at the top, so?
No, mass is constant.
What about the height? No,
Height is constant, 12 inch.
Is it because although our eyes increase, eyes bigger, but the mass of the eye as well?
Mass is constant, but I is increased. Yeah, I is in the denominator, and I really decreases sigma. But really, what has increased sigma is the n, the bending moments. The bending moments. The answer relies on the aesthetic shape of this graph. And the answer is, let's take a look again. First case, first trial, second trial. Smaller section, bigger section. In both cases, mass is constant, okay? Mass is constant in both cases. What is changing? Stiffness. Because the stiffness is changing, omega n changes. Omega n changes, Tn changes. In the first trial, it's 1.59 seconds. In the second trial, it's 0.5 seconds, right? what we do with this Tn, what really we do is to go to the spectral acceleration shape and read a number, bring it in, multiply it by the mass, which is constant. When your natural frequency in the first trial is 1.59, you're reading this number. When your Tn is 1.59, you're reading this number, 0.2. But when you're in the second trial, when your Tn is 0.5 second, you're reading this number. That's why you're bringing 0.8 instead of 0.2 into calculation to be multiplied by the mass, to be your bending moment, to contribute to the sigma max, to produce that stress, to be compared with Fy. It means there is a very important dynamic behavior for the structures, which we usually don't admit. We usually think in the static environment, like the force is constant, the structure should be bigger to be okay in the design phase. But the reality is, in the dynamic environment, when you change your structure, you're influencing the external force as well. If you take a bigger, a tougher, a more stiff structure, rather than a flexible structure, you're increasing your internal force as well. The earthquake, for some reasons, for the reason of omega and for the natural frequency, will induce more, will pump more forces into your structure. And the resulting stress is more. What you should really do in practice, in practice, if it's not okay and you are stuck to use that kind of steel, okay, you need to go for the third trial and really bigger your section. Because with that section, you're really here at the toppest ever you can be. If you really bigger your structure, you cannot be more than this. You will be probably here. You will come up with some lower parts. But it still means you need to bigger your section even more than you have done in the second trial. You need a very gigantic section for your design. So it means that changing with your structural properties, especially stiffness, will influence your external forces as well. It is not the case in the case of wind loads. The wind load is really depends on the geometry of your structure, how wide, how tall your structure is when the wind blows, the resulting forces, how obstacle you're making in front of the wind, so you will get some forces. But in the case of earthquakes, seismic load in Eurocode 8, it's totally different. The induced force into your structure depends on the mass and the stiffness. You, as a designer, you don't usually have too much flexibility to play with your mass. Because mass is mass. You need some walls, some floors, something. So mass is relatively constant and out of your hand. But the stiffness is in your hand. And when you play with this stiffness, you're playing with the external forces coming into your structure. That's why this the increase in the section property doesn't solve the problem in one go. You need to go for a third case as well. Do you need a break, short one or not? But you have yours, the others. You want a short break or we continue? It really depends on you. You vote. No? You want? No? No? Okay. You want, I know, but it's not the case for you. Okay. Example 3. Sorry, the next example. I said there are 4 examples. Yes. The first 2 examples work together. The first 2 examples were designed just to show you how the stiffness can play with your external forces. But another concept, dynamic concept, is inherent in the examples 3 and 4. Yeah, 4 and 5. This is a 1-story building. This is a 1-story building. Reinforced concrete building is idealized for purposes of structural analysis as a massless frame supporting a total dead load of 10 kips at the beam level. Okay. So the mass is 10 kips. This is the mass. We are neglecting the mass of the frame in terms of the mass of floor. Slab mass is dominant, so the mass of 2 columns is really negligible. It's not a big deal. And the frame is 24 feet wide. This is the wide, 12 feet high. Each column and beam has a 10-inch square cross. So they are like this, 10-inch. This is 10. Assume the Young modulus equal to this one. This is the E. The damping ratio 5%. This is psi. Determine the peak response of this frame to L central ground motion. Stop here. Peak response of this frame. Peak response means peak deformation, peak velocity, peak acceleration. But usually we are interested in peak deformation and peak acceleration, just to multiply by mass to be a design force. The process here is exactly like we have done with that water tank. You have a mass. You need to calculate your stiffness, come up with your omega n, and get your Tn, go to the graph. Go to the Excel, read the acceleration, bring it in, multiply by mass. You will get your force, right? What we can do is, here, because the beam is not rigid, we have used this formula that we had this probably in the first lecture. Maybe I can quickly find it just to recall you what lecture was it. Matrix analysis. Probably this one. This one. This one. 134. Equation number 134, 96/7 EI column over H3. I'm using this formula. When you have a single story, 1 bay frame like this, and the slab is not rigid, you have beam there, the horizontal stiffness is this one, coming from this. And okay, this is the lecture number 6, the first lecture in the new subject. So we are using that formula for the stiffness. And with that formula, we come up with the stiffness. We have the mass is 10 kips, and we can calculate the Tn or omega n, doesn't matter, this is omega n. Okay? If we calculate Tn, you will come up with 0.3 second. Okay? With 0.3 second, you can go to your Excel and it's really somewhere here. You will really read something like 0.60 something. If you, let's see what the book has put there. It's 0.76. The book has read this number from itself. Okay? So this is your spectral acceleration, and you know always the spectral deformation is, spectral acceleration is omega n2 spectral deformation. So if this is 0.76, you have omega n, you can come up with SD, spectral acceleration, which is 0.67 inch. It means that if earthquake, the epicenter earthquake occurs, ground shakes, this one-story building will shake, and the maximum deformation during the, 30 seconds of the earthquake will be 0.67 inch. And the maximum acceleration is 0.76 g, which means you just multiply this by the mass to come up with your design force, right? The second part says, plot the diagram of bending moment at the instant of kick response. So this is the last part. It's questioning. When you have your force, this is the force multiplying the spectral acceleration by the mass. If you have that one, the force will be divided into half parts, one for each column, right? And for each column, it's like divide 7.6 kips into two parts for your both columns. And for each one, multiply that by height, and you will get the distribution of bending moments like this. And the point that this example, and absolutely the next example is going to emphasize, is that in this example, the internal forces for both columns, the internal bending moment is similar. What you get is similar for both your columns. However, see what happens if we move to this example, which is really similar to the previous one, but it is going to be constructed on a sloping ground for some reasons. And for that reason, one of the columns should be 12 inch, but the next one should be 24 inch, because the ground is like this, right? And this is common practice in many regions around the world. You're using some, you're constructing some building on a sloping ground, so see what happens when an earthquake occurs and what will be different from the previous case. If you repeat the whole steps in this example, the only difference is calculating K, because the columns are not the same. So for this example, it's assuming that the beam is very stocky and the slab is rigid, so it's not going to use that formula 96/7. It's going to use 12 EI over L cubic. So it means that the slab is rigid, so it's using 12. But for different columns, we are using different height. Where is the height? This is the height. This is the height. 12 and 24. That 12 is coming because it's transferring foot to inch. So you can imagine for the stiffness, you have L cubic in the denominator, right? So if you have 12 inch or 24 inch, which one has more stiffness?
12.
This one, because 12 is in the denominator, here 24 is in the denominator. The difference is 8 times, because you have cubic here. When the height of your two columns are 2 cubic means 8. This is something, this is something. But if the total is 9, one part is here, 8 part is here. Right? It means that this column is way far more stiff than this column. How far? 8 times. If the total stiffness is 9, let's call it, 8 part is this one part is this one. Right? What's the fact? If you calculate K, you can see it's 10, this term is 10, this term is 1 point something. If you calculate K and you have the mass, you can come up with Tn, which is 0.3 seconds, something similar to the previous case. And again, if you go to the Excel and read the numbers, you will come up with relatively the same thing, You know why we are coming up with relatively the same thing? Because the only difference from this example with the previous one is this column. And this column is not so stiff as to contribute too much in the stiffness. It's a very small number, so everything is more or less the same than the previous case. More or less, although you have a longer column here. Everything is almost the same. That's why the natural frequency stays more or less the same. Whatever we read from the Excel file stays almost the same. The point is, when you calculate these stuff until here, everything is the same. But after that, it's like this is F, which is this one multiplied by mass, right? But the question is, how this F will be distributed into these two columns. You have two ways to calculate it. The first one, this, you can use any kind of approach you have learned in the structural analysis. Okay? You can say this should be proportional to the stiffness of these two columns and stuff like that. But I don't want to go with this case. I want to go with the second approach. The second approach is the maximum deformation is this one. This is the maximum deformation during error. What does it mean? It means that this deformation will occur, and this is, the slab is rigid here, keep in your mind. This is 0.67 inch, and this is 0.67 inch. The deformations are the same because the slab is rigid. I can say, when I know the deformation of a column, and I know the stiffness of that column, you know the force inside this column is the stiffness that and multiplied by the deformation. You have the stiffness for this column, you have the stiffness for this column. Bring the stiffness for each column, multiply it by 0.67, and you will come up with the internal force into this column. And since there is a huge difference between those stiffnesses, you will get a big portion of the total force in this column and a small portion of force in that column. And it means that for the short column, you will come up with this number, for the long column with this number. If you design your short column for something like 8 times of this one, you should come up with a relatively big section for the left column and relatively small section for the right column, right? Have you ever seen such buildings on a sloping ground with the same columns everywhere? I have seen many times. It's common practice because, not in the UK, probably, I'm not sure in the UK, but in many countries around the cities, there are some illegal constructions made by people. And it's, it's very widely spread that sometimes the government cannot stop them. And sometimes they don't want to stop them because they just get something illegally from them just to leave them alone for themselves. And they just construct a building overnight sometimes, because that's one-story building overnight or two. They just complete it and they live in it with some children and nobody can touch it. So it's the case in many parts of the world. And you can imagine when they do the construction without any engineering background or something, they just do the columns, whatever steel columns, it doesn't matter if it's a steel or concrete. They do the same section, they just go to the market and buy some steel profiles, bring there and cut them and just construct whatever they want. And there is no background on the process. And they use the same column for all of the structure. And they don't realize that in the case of earthquake, the external forces can go far differently into different columns. And they can break this column at the first instance.
I think sometimes I've seen it, so sometimes what they do is they might have the same column section, but they rotate the column around, change the direction.
That's another problem. That's another problem. If you have two frames that you need biaxial moments, I mean, you have two moments, and of course an axial force, that's another problem, yeah. We are talking about a 2D here, but that problem is in 3D, so we have two bending moments as well. Yeah, this point is that this point is going to focus on the fact that the forces from earthquake is not going to proportionally distributed to all columns without any difference. So if you have different columns with different height, the internal forces will be very different, can be very different based on this fact. And that's the point. So if you have noticed in the news during the earthquake in Turkey, the recent earthquake in Turkey, in Syria, it was a disaster. A lot of buildings were collapsed. In addition to this fact I told you, there were official procedures between people and government to pay government and councils, and they don't look at the codes, safety codes they have used for their buildings. So they were legally eligible to pay to the government and council and not follow the design codes. That's ridiculous and pity, and that's the reason it results to such a big disaster. So you can find in the recent earthquake, you can find many structures, like concrete structures, they are collapsed totally, and when you see the pictures, you don't see much reinforcement there. You just see 4 reinforcement in column in a 15-story building. So it's impossible to design a 15-story building with the columns of 4 reinforcement, 4 very small reinforcement. They just skip the regulations legally by paying the government and councils some money just to let them to bypass the regulations for the safety. And because sometimes some people picture this disaster in a way that the most problem comes from the codes. It's not the case. Many of the structures that comply with the code still stand there. If anybody comply with the design codes, the Eurocode, nowadays every country has a code. If it doesn't, you can use the United States code, because United States code has a part which claims that I'm going to recommend the loading for any parts in the world.
So there's a Eurocode, no?
Eurocode, I don't know. I'm not sure now. The Eurocode, the American code, actually the design code is okay. You can use whatever design code you want in if you live in any part of the world, you can use Eurocode, American code, but the loading is different. The loading is different. The American code for loading has a part, for example, for seismic load or wind load, whatever. They say, okay, because Americans claim that they think big, they act big. So they have this philosophy that they say if we write the code for ourselves in the United States, we put a section there just to put some parameters for other parts of the world. If any engineer wants to design a structure in, I don't know, in Africa, they have some numbers here to be used in that region of the world. It's a good thing actually, because if they are living, I mean, I said this because I want to emphasize that no engineer can say I don't have design code to be used. If you don't have use of design code in your country, use the United States code.
Have you used the ASI? Yes.
ACI?
Yes.
Yes, for years. ACI for concrete, AISC for steel, and Uniform Building Code for loading the structure. Yeah, I've worked with American code for years.
Is it more difficult than the Eurocode?
It's more complex, not complex, but yes, it is more complex. But it is better designed, it's more clear. But apart from only one part, which I think Eurocode is probably better, which is the shear design. We didn't discuss. We discussed in the structural design. The shear design in the Eurocode is somehow totally different from the American, with two different perspectives. If you design shear reinforcement with the Eurocode, you will come up with quite a lot of reinforcement rather than American. Apart from this one, the other things is it's more clear, more probably more advanced. I think so. But for the shear design, Eurocode is better probably. At least more conservative, let's say. Just a question for me to better understand, because here is the place that I don't have enough time today, but I will continue with the Eurocode 8 to see how these stuff will be implemented in the Eurocode. I want to know how much so far you know about Eurocode 8 and seismic loading and structure, and in which modules you have implemented them.
We haven't used Eurocode.
At all? Okay, so it's totally new. So for different design examples, you just used wind load, right? As lateral loads.
Are you talking about the coursework? Or?
Any project, coursework project, I don't know.
We have used wind loads for last year's coursework.
For this concrete,
Yeah, concrete.
What kind of loading you have? Today you have coursework, I don't know. What kind of loading you have?
You only have variable load and permanent.
Okay.
You don't have any snow. Wind.
Okay. So you haven't had any kind of lateral load like EC8, so it's not bad. It means that it's an opportunity to learn a little bit about Eurocode 8 for seismic loading. So it's good. And we have a few slides just to illustrate how the Eurocode deals with the problem. And also we have 8 slides here to learn about the Eurocode 8 and the implementation of these stuff in Eurocode 8. And also I have prepared a very simple spreadsheet here. It is already on the Moodle, and I will leave them for the next week, but I just want to show you the shape of the figure. This is the shape that the Eurocode proposed to engineers. So if you see what we have got from El Centro, it's this one. The Eurocode, the codes need to smooth things for the engineers, right? If I want to smooth this, I will smooth like 1, 2, 3, right? So this is what the El Centro is, and consider that the El Centro is not only earthquake around the world. We have a couple of hundred earthquakes around the world, 1,000 earthquakes. So in reality, you need to take into account other earthquakes as well into consideration. So if you take them, you will have some figures like a little bit different with this. You can make an average over them, and if you do some stuff like that, you can smooth them like this, and this will go to the Eurocode to be like this. And this is what the Eurocode proposes to the engineers. A very beautiful shape, and this has really principally 4 parts. 1, 2, 3, 4. Forget about this part. This part is because I wanted to calculate for this number, otherwise it's a smooth. 1, 2, 3, 4. And each part has a formula. This is formula for this part, this is formula for this part, this is formula for the third part, and this is for the fourth part. And there's a beautiful shape for a spectral acceleration. Eurocode proposes to you, and there are some parameters. The parameters coming from the soil type, etc., like that. If your soil is like that, this one is that, you will see it next week, okay? You can figure out these parameters, put in these formulas, you will get this shape. And if you have your structure, very complex structure, if you would be able to calculate the natural frequency, this is your coursework. The building, calculate the natural frequency. A multi-degree freedom system, calculate the natural frequency. If you're able to calculate the natural frequency, okay, you have a number, Tn, natural frequency. Bring your number in the x-axis. Where is it? Okay, it's here. Read the spectral acceleration. This one, as we did today, multiply that spectral acceleration by the mass, you will get your design force. That's it. This is the whole procedure that the Eurocode 8 works, right? For seismic design.
Where did you get these beautiful equations from?
Where did I get? They are from Eurocode.
Oh, they're from the Europe now.
Eurocode. They are the questions of the Eurocode. Yeah. They are in the Eurocode 8. You will see the same things. I just cut them, paste them here.
Are they in the slide? The equations.
Yes, they are, I think. Yes, they are here. Yeah. For example, here, based on ground type A, B, C, D, E, the soil type, actually, you will get some parameters, put them into here, and you will come up with those kind of shape. So I also put, as you see, I also put everything together in the Excel, and the numbers. If you change anything, it will be changed. So this is the shape of spectral acceleration in the Eurocode 8. And that was my aim to conclude today, that the whole procedure from the start of partial differential equation, we started in the 3rd session this term. We spent 2 sessions, I think, for the remaining stuff. From after the matrix analysis, we started with the partial differential equation. We proceeded to the earthquakes, with the numerical method and stuff like that. Today, we put everything together to come to this point that it's really what you see in Eurocode 8. So personally, I think it's very important, and it's beautiful to see when you, from 0 to 100, from partial differential equation, you progress to see it enters the Eurocode, and it's proposed to design engineers to be used in the design offices. This is the whole procedure for engineering, and this is the target for the engineer, to simplify everything for the design engineers to be used in the design offices. That's the art of the engineer. So this is the Eurocode 8, that if you want to load your structure for seismic loads, you need to simply calculate the natural frequency of your structure. This is your coursework, again, I emphasize. And if you have your natural frequency of your structure, you simply come here, get your number, multiply by the mass, you have your design force, and you will analyze your structure based on design force. You will get your internal forces, analyze it simple, either by ETAB or by hand calculation, and you can design your structure and check the safety if it's safe or not. This is the whole picture of Eurocode 8. So, due to the time limitation, I will leave these 4 slides to the next session to be better discussed. Okay? Any question for today? The Excel files are on the Moodle. Please download them, play a little bit with them to see, to get used to them and to see if there is any problem. It's not guaranteed there is not any problem. I've done them, so I might have some errors. Just check them again. If there is any question, we can discuss next week as well. Otherwise, have a nice rest of the day and see you next week. Just a reminder that not next week. Next week is lecture. The week after that is mock test. I will send emails about that. The week after that, 31st of March, we will have 2 sessions. One will lab. We have lab in that day. One will be in the lab, 2 hours, and then we come back here for another 2 hours section.
Mock test done.
No, next week is lecture. The week after is mock test. The week after is 2 hours lab, 2 hours extra session here. Okay? And the last week is Good Friday. We don't have. 8th of April, we don't have class. Right? Yeah. 8th of April, 7th of April is the last Thursday, last day of the semester. 8th of April is Good Friday, it's off. So the last session will be 31st of March with 2 sessions, 2 hours lab and 2 hours lecture. Okay? And that would be last lecture of the semester. But in 2 weeks we'll have mock test. Not the next week, the week after. Okay?